field will go perpendicular to the paper. In this case, I think I'm right saying the magnetic field will come transport the paper. I've got that right. It's essentially a one-turn solenoid. That's all it is. And the solenoid produces a magnetic field. It's just one turn, so you can get a magnetic field. And you get a magnetic moment, which is defined as the current times the area. Now, you can think of an electron orbiting a nucleus. There's a nucleus. There's the electron. The electron is traveling at speed v, which of course is changing. It keeps an absolute value of v, but it changes direction. The radius of the orbit is r. We'll say the mass of the electron is m. And what we can say is the angular momentum of that electron, or angular momentum is ordinary momentum multiplied by the distance from the orbiting point. So the ordinary momentum is mv, the momentum is mass times velocity, and the distance from the orbiting point is r. So L is mv. R, that's the angular momentum of the electron. The current is defined as charge divided by time. So that's going to be E, which is the charge of the electron, divided by the time, which is the time it takes for the electron to do one complete orbit. Because every orbit it comes around again, you get more charge flowing. So you get a charge of E flowing every t seconds. The velocity of the electron is just the distance travelled divided by that time. The distance is just the circumference of the orbit, which is 2 pi r, and time is term t is here. So I can rearrange that to say that t is 2 pi r over v. So now I can substitute that t in here, and that gives me that the current I is E divided by t, but t is 2 pi r over v. So far, so good. Now the magnetic moment is the current times the area. So the magnetic moment for this electron is going to be the current, which is ev over 2 pi r from here, times the area, which of course is pi r squared. So the pi's go, and one of the r's goes, and you're left with EVR over 2. So that is the magnetic moment of the electron, which is orbiting the nucleus. We are being very practical here, of course. Now I'm going to multiply top and bottom by MVR over MVR. Right, so I can MVR over MVR is simply 1. And I can always multiply anything by 1. But MVR, of course, is, and the reason I chose it, is the angular momentum L. So that MVR, I'm just going to call L. This V and this R cancel that V and that R, and that gives me E times L, the charge of the electron times the angular momentum, divided by 2 times the mass of the electron, is the magnetic moment. Now, Bohr introduced a concept, Niels Bohr, of the so-called Bohr magneton. And the Bohr magneton is defined as EH bar over 2m. So that's a definitional term, it's called the Bohr magneton. And on that basis, the magnetic moment of the electron is going to be, well, if you've got the E over 2m part, that's here. So you just need the Bohr magneton multiplied by L here, but you can see H bar, so you divide that by H bar. And that now becomes the magnetic moment for the electron. The Bohr magneton, which of course is just a constant. It's the charge on the electron times any constant times twice the mass of the electron, that's all constant, multiplied by the angular momentum divided by H bar for an electron. And you won't be surprised to know that you can do exactly the same thing for a proton, even though classically the analogy doesn't work. And so that the magnetic moment associated with the angular momentum for a proton will be what's called the nuclear magneton times L over H bar, where the nuclear magneton is not like the Bohr magneton. It's EH bar over 2m, so a little T there. Well, that means if E is the charge on the proton, which is of course the same as the charge on the electron, but just with an opposite side, H bar is the same, and this is now the mass of the proton, where it's the mass of the electron, so very similar in concept. So this gives us the magnetic moment for the proton associated with the orbital angular momentum. Now you might also think that you could do these two terms in relation to not the orbital angular momentum, but the spin or angular momentum. So you might think that the magnetic moment of the electron, when it came to the spin, which is right there, when it came to the spin element would be the Bohr magneton times F over H bar, which would have well be a mirror image of this here, instead of L, you said it was S. But actually, that is not right. There is, in fact, a number that comes in front of this. It's actually almost twice as much. It's 2.0023 times the Bohr magneton times the spin divided by H bar. And that can actually be derived, I'm not going to do so, from the Dirac equation. And you might think, therefore, that there will be a similar magnetic moment in relation to the proton for the spin term, and indeed there is. But it has a different value. In fact, whether it's the proton or the neutron, we usually say that it has a value G times the nuclear magneton times F over H bar. For the electron, G as it was minus 2.023. For the proton, G for the proton is 5.585691. It's estimated to that level of accuracy. And G for the neutron is going to be equal to minus 3.826084. And why are they different from the electron? And why has a neutron got a magnetic moment anyway when it is uncharged? And the reason for the difference, of course, is that an electron, as far as we know, has no structure. It is a fundamental particle. It is not made of anything smaller. It is just heat. Whereas we know that a proton actually is made of quarks, 2 up quarks and a down quark. And a neutron is also made of 3 quarks, 2 down quarks and an up quark. And those quarks have charges. An up quark has a charge of plus 2/3 of the charge of an electron or a proton. And a down quark has a charge of minus 1/3 of the charge of an electron or proton. So 2 ups would be 4/3, minus 1/3 gives you a charge of 1 plus 1 for the proton, so that's where the proton's charge comes from. Whereas 2 downs is minus 2/3, plus an up is plus 2/3, gives you an overall charge of 0. So that's why the neutron's uncharged. But look, inside these two, you have got charged particles. There are charges. It's only going to say that from a distance, the effect is that the proton is charged plus 1 and the neutron is charged 0. But that neutron has charges within it, and they, as they're orbiting, will create a magnetic moment, and that's why you get a magnetic moment for the neutron. It also explains why these are different, because you've got a different distribution of charges. Here you've got 2 lots of 2/3 and minus 1/3. Here you've got 2 lots of minus 1/3 and 1 plus 2/3. So you're going to get a different value of G in the equation. So what happens if we want to know what the spin of the deuteron is, the combination of the proton and the neutron? Well, you might think that that will be the nuclear magneton divided by 2 times G spin for proton plus G spin for neutron. And that comes to the nuclear magneton divided The two values I gave you before, which were the proton 5.585691, the neutron minus 3.826084, and you add those two together, you get 5.58 minus 3.82, the actual value is 1.759607, and that comes out to be divided by 2, 0.87980 times the nuclear magneton. But this value of magnetic moment for the neutron can actually be measured experimentally. So if you do the experiment, you find the value comes out to 0.8574 times the nuclear magneton, which is good. That's the theory, that's the experiment. The experiment always dominates. You always have to adjust your theory to accommodate the experiment, not the other way around. It's not a bad fit, but it's clearly not right. What has gone wrong? What do we assume that we shouldn't? Well, of course, what we did is we assumed that there was a spherical potential. So spherical potential is associated with the orbital angular momentum L equals 0. Maybe there is an L equal 1 or an L equal 2 term stuck in that potential. Well, if we come back to what we said before, there cannot be an L equal 1 term there because the parity, remember, was measured for a neutron as even. And if it's even, the values L can only be 0, 2, 4, 6, and so on. So if there is another orbital angular momentum term in there, it has to be L equal 2. Since things are so close together, it's probable that we wouldn't have to go up to higher energies L equal 4 and so on. So let's establish whether there could be an L equal 2 term in there. But what we would be saying is that the total magnetic moment of the neutron, measured experimentally, would be equal to a proportion of L equals 0 plus a proportion of L equals 2. And of course, those proportions must add up to 100%. That means that A plus B must equal 1. So effectively, what you're saying is that the experimentally measured value, 0.8574, is going to be equal to A times the L equals 0 predicted value, 0.8798, plus B times the L equals 0 value. That gives us two equations, A plus B equals 1, this equation here with two unknowns. I mean, for B, you can simply substitute P equals 1 minus A. And you can solve then for A and D. And what you'll find is that A comes out to be 0.96 and B comes out to be 0.04. From which we conclude that 96% of the potential is genuinely an L equals 0, a spherical potential. That's why the spherical potential is giving us good results, because it's 96% it is. But there is a 4% contribution of an L equals 2 orbital angular momentum term. So from that we can now conclude that the nuclear potential is equal to quite a lot of spherical potential. Now we know that we must have a little bit of non-spherical potential, and then as we speculated earlier, there is a spin term as well. So now we're starting to build up the component parts of the nuclear potential. So today we're continuing our series on nuclear physics, looking at nuclear scattering and spin. What is the technique that physicists use for investigating what is going on at nuclear level? Well, it's the slightly unsubtle way of bombarding a target with projectile particles. These are the projectiles, this is the target. You hurl projectiles along at very high energy, you smash them into a target, they come flying off in all directions, sometimes even backwards, and what you tend to do is to measure the number which come off at a particular angle, and you move the projectile all the way around, so you get a distribution of the number of particles coming off at a particular angle. Some people say this is a bit like trying to look to see what's inside your watch by taking a hammer. You smash the watch, all bits inside the watch come out and you can see what's inside the watch. There is one important difference, that when you smash the watch, it's very silly thing to do, if you smash the watch, you only see the bits that were in the watch in the first place. When you smash subatomic particles into a target like this, sometimes you actually create particles which were never in the target in the first place. This is because some of the energy associated with this incoming projectile is sufficient to create new particles. So that's the additional dimension here. We'll be looking at fairly low energy, but at least for the time being, so we're not too worried about creating new particles. We're simply looking to see if you send in a projectile beam, what happens to it, how is it deflected, as it goes to the target. Now, in my video on nuclear radius, which is in the playlist on nuclear physics, you'll see that I introduced the concept of cross-section. What I said was that if this is a kind of a nucleus, and you've got a projectile particle coming some distance from the nucleus, then it probably will only be deflected by a very small angle. Whereas if you've got a projectile particle coming very close to the nucleus, it will be impacted much more, and its angle might even be greater than 90 degrees, it might be sent back. And that from the point of view of the incoming particle, you have what's called cross-section. If you want to leave this particle here, being deflected through a small angle, then you've got this kind of area to aim at. Whereas if you want to leave this particle, you've got a much smaller area to aim at, because you've got to get very close to the nucleus. And this is the concept of cross-section. This is a large cross-section, because you've got a lot to hit in order to be deflected to a small angle. This is a small cross-section, because you've got a very small area to hit if you want to be deflected to a large cross-section. So cross-sections are measured in areas, and they're usually measured in the units of a barn, as in the barn that owls nest in. It's called a barn, and it has a value of 10 to the minus 28 meters squared, so it's generally a measured area, but a very small measured area. Now, so far in this series, we considered a bound neutron, a proton and a neutron bound in a neutron. Now we're going to consider something slightly different. We're going to consider a beam of neutrons, that's our projectile particle, hitting a target which has protons within it, and we're looking to see how the neutrons are scattered. Now in passing, for those of you who are asking, how can you get a beam of neutrons? We know how you get a beam of protons, that's not yet. In theory, if you put a negative charge, a positive charge here, and a positively charged proton here, the positively charged proton will be repelled by the positive plate and attracted to the negative plate, and you've got a little hole in the plate. The proton will be traveling faster, 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 gets through the hole, and you've got a fast moving proton. You just apply a series of electrically charged plates. But if you've got a neutron, that won't work, because the neutron is not going to be attracted to positive or negative plates because it doesn't have a charge. So the way you have to do it, the way of doing it, one way of doing it is actually to fire protons, which you can accelerate at a target. That will, of course, produce a whole load of rubbish coming off in all directions. But the bulk of it, of course, always comes off in the forward direction. If you look at the number of particles coming off in forward directions, it's hugely more than that which is deflected. Those particles will do all sorts of things. So if you put an electric plate Now, a lot of those neutrally charged particles, like pions, they will decay very quickly. And what you find is that the bulk of what's left is a stream of neutrons. So, of course, those neutrons will have a whole variety of different energies. You cannot create a single energy stream. But since kinetic energy is half mv squared, then the higher the energy, the higher the velocity. And the higher the velocity, the sooner that neutron will get to the target that you're actually aiming at. This is the neutron beam, this is the target. So the neutrons that get there first will be the highest energy. And then the neutrons that arrive later will be at lower energy. And of course, the electronics are set up such that they measure the time for all these bursts. So you know when the neutron hits the target, how long it took. You know the distances, you can calculate the velocity, you can calculate the energy of the neutrons over time. That's the way it's done. Or at least I would say that's one way it's done. So let's go back to our famous diagram for the nuclear potential. I've drawn this many times now. The nuclear potential is plotted on this axis. The separation of the proton and neutron on this axis. This is R0, which for a neutron remember was 2.130. This is 0, and this is the nuclear potential in the neutron, which was minus 36 MeV, and we call that V0. When we were talking about the neutron, we put in a binding energy, which was minus 2.225 MeV. But now we're talking about firing neutrons at a target containing protons. That is now our experiment. These are individual neutrons which are being fired at a target containing individual protons. We're not talking about a neutron anymore. We're still talking about a neutron-proton interaction. So the interaction is still going to be the same, but they are no longer bound. Indeed, the energy of the neutron is up here. So instead of having a binding energy, which is a minus term, we've now got a positive energy because the neutron is free. Once again, we can talk about two regions, the region inside the nuclear potential and the region outside. And now we go back to our old friend, the Schrödinger equation, which we've used so many times in our videos in this series. Minus a bar squared over 2m times d2 psi by dr squared plus d psi is equal to e psi. That's the time independent Schrödinger equation. And you may recall in an earlier video I pointed out that the mass is the reduced mass of the combination of the proton and the neutron. So we can rearrange this formula to say that d2 psi by dr squared is equal to minus 2m over h bar squared into e minus v psi. That's just rearranging this. You take this over to this side, so it's upside down, 2m over h bar squared with the minus, and then you bring the v over here so it becomes minus v, and that's the rearrangement of the Schrödinger equation. Then we say for region 1, where the potential is V0, so D is V0, we can say that for region 1, d2 psi by dr squared is minus 2m over h bar squared into e, which of course is the energy of the neutron, minus V0, where V0 is the depth of the nuclear potential, times psi. Region 1. Region 2 is the region where there is no nuclear potential, D is 0 here. So we've got d2 psi by dr squared is equal to 2m over h bar squared, e minus nothing, so it's just e times psi. Now as I did before, I'm going to put a box around these two terms, because I want to persuade you that those two terms are both positive. E minus v. Well, d is a positive term, v is a negative term, so you've got e minus a minus term. A minus minus is plus. So e minus v0 is e minus 36. So that's e plus 36. So e plus 36 is positive. Similarly, e is already positive, so this is a positive term. Consequently, we can do the whole trick of calling this a squared and this l squared. And the reason we wanted these terms to be positive was that then k and l will be real numbers, not imaginary numbers. So the minus terms are left on the outside. And that means we essentially and the way of writing that is a sine kr plus b cosine kr. That's for region 1. And for region 2, also oscillatory, that's going to be here. That is going to be c times sine lr plus d times cosine lr. Now for the first region, we can say, all the way back up here, when r is 0, the wave function has to be 0. So when r is 0 in region 1, r is 0 is 0 in region 2, of course, because region 2 doesn't start till r equals r naught. So we know right here, when r is 0, the wave function is 0. Sine kr will be 0 because the sine of 0 is 0. The cosine of 0 is 1, so b times 1 is b, so b equals 0. Consequently, that term goes if b is 0. And in region 1, this is the value of the wave function. But you can't do that for region 2 because you haven't got an r equals to 0 in region 2. So you have to stick with those terms. But I hope to persuade you that that is one and the same thing as e times the cosine, sorry, d times the sine of lr plus delta, where delta is a phase angle. And how can I demonstrate that to be the case? By looking at the identity, which says that the sine of x plus delta is equal to sine x cosine delta plus sine delta cosine x. You can look that up on Wikipedia or Google. That is a standard geometric, or trigonometric, should we say, trigonometric equation. plus delta, and d LR0 plus delta are all part of the defined cosine function. And if I regard this as equation 1 and this is equation 2, what I'm going to do is to divide equation 2 by equation 1. So I'm dividing this by this. A is going to cancel out, and what I'm going to get is k times the cotangent of k R0 is equal to this going to divide by this, and the e is cancel out, and I'm going to get L times the cotangent of LR0 plus delta. I'm going to remind you that we know what k and L are. K squared is this, L squared is this, so k and L are just square roots in each case. We know the mass, we know the energy, that's the energy of the neutron. We know V0, that's the depth of the potential well. Here we just need to know the energy of the neutron. So all the k squared and all the L squared are known. We know R0, that is 2.1 fermions, so we know everything in that equation apart from delta. And that means we can calculate delta, the so-called phase angle. I'll explain more about phase angles in a little while, probably in the next video. And how you can solve for the value of delta. Now it turns out that that value of delta is related to the cross-section. By this formula, we will not dwell on how you get to it, because that's not the point we're trying to make in this video. So the cross-section for a particular angular distribution is for low energy, and this is what we're talking about here, 1 over k squared sine squared delta. Okay, that's what we're doing, direct cross-section for a particular value of theta, which is handled with the cross-section, or among the total cross-section for all angles, which is the integrated version of this, and that comes out to be 4 pi over k squared sine squared delta. So delta, you can see, is related to the cross-section. So if you've got delta, you can calculate the cross-section. And if you can calculate cross-section in this case, neutron proton scattering, you get 5 barns. Barns, remember, is a unit of area, and we said that 1 barn is 10 to the minus 28 meters. That's small cross-section. But when you measure it experimentally, and this is now the experimental measurement, you get 20 barns. So the theoretical derivation and the experimental derivation are significantly different. Something's gone wrong. What has gone wrong? Well, you remember that when we spoke about the neutron, we spoke about the potential, the nuclear potential D. This is 0, this was the binding energy, this was the depth of the nuclear potential. We speculated, if you remember, that you would have an x equal 1 contribution in this nuclear potential, and it's contributing to it, but that you couldn't have an x equal 0 because we speculated if you did, the nuclear potential would be as deep. Consequently, the neutron would not be bound because the binding energy would be up here somewhere, and therefore you wouldn't have a neutron, you would just have a free neutron and a free proton. So we said you can't have an x equal 0 term in a neutron, you can only have an x equals 1 term, because if you have an x equals 0, it's not bound. But now we're talking about neutrons scattering off of a proton target. They are bound. This is not a neutron. So this arrangement can have an x equal 1 and an x equal 0 effect going on, because they're not bound. The only reason you didn't allow x equal 0 in the neutron was because it's bound. We showed earlier that there are 3 states of the x equals 1 state at 1 h bar, 0, and minus 1 h bar, each separated by h bar, whereas of course there's only one state for the x equals 0, spin, and that's 0. So there are 3 times as many states for the x equals 1 as there are for x equals 0. Consequently,